Have you ever stopped to think about the hidden brains inside your tech? The things that make cruise control work or a thermostat keep the perfect temperature. Well, they're called control systems, and they're like these invisible intelligences making thousands of decisions every single second. Today, we're going to pull back that curtain and see exactly how they do it.
Okay, let's dive right in. To really get how these systems work, we first have to wrap our heads around the basic problem they're all trying to solve. And that is, how do you make something do exactly what you want it to, when the real world is constantly trying to mess things up?
Really think about it. You lock in your speed at, say, 65 miles per hour. A second later, you start going up a hill. Then you come down the other side. A big gust of wind hits the car. And through all of that, somehow, the car stays perfectly locked at 65. How on earth is that possible? Well, what's really happening is that the system is in a constant fight. The engine is pushing you forward, sure, but you've got these invisible forces like friction and wind pushing you back. Then you go up a hill, and suddenly gravity is working against you too. The car's brain has to be smart enough to counteract all of that, instantly. And here's the secret weapon that makes it all work: the feedback loop. It's pretty simple, really. The controller, which is the brain, tells the plant, that's just the thing being controlled, like our engine, what to do. A sensor measures the car's actual speed. Then, that measurement gets fed back and compared to your goal. The difference between the two? That's the error. And the controller's whole mission in life is to get that error to zero. So how does the controller decide how much gas to give it? The most intuitive way to start is with something called proportional control. It's a great first step, but as we're about to find out, it has one major flaw. Proportional, or just P control, is built on a really simple rule. The bigger your mistake, the bigger your correction needs to be. So if you're 10 miles per hour too slow, it floors it. If you're only 1 mile per hour off, it just gives a little nudge. It only cares about the error happening right this second. So what happens when we let P control take the wheel? Well, it reacts so aggressively that it just blows right past the target speed. Just look at that huge peak on the graph. It overshoots by a massive 57%. That would feel incredibly jerky and uncomfortable in a real car. Now, you might be thinking, okay, easy fix. Let's just make it less aggressive. Just turn down the power. And yeah, we can do that. But then we run into the complete opposite problem. The car takes forever to get up to speed. It feels sluggish, unresponsive. We've just traded one problem for another. This data here shows that trade-off perfectly. As we lower the controller's power, or its gain, the overshoot gets smaller, which is great. But look at the rise time. That's the time it takes to get to speed. It just skyrockets. With P control alone, you simply can't have both. You can't have a fast response and low overshoot. Okay, so this is where the real genius of control theories starts to shine. If reacting to what's happening now causes us to overshoot, what if we could somehow predict the future? That's the whole idea behind our next piece of the puzzle: derivative control. Derivative, or D-control, is totally different. It doesn't look at how big the error is. It looks at how fast the error is shrinking. If it sees your speed rushing towards the target way too quickly, it knows you're about to overshoot. So what does it do? It starts easing off the gas, kind of pumping the brakes, before you even get there. It's all about anticipating what's coming. And the effect is, well, it's absolutely dramatic. On the left, you're looking at an overhead crane with just P control. It's a complete disaster, swinging back and forth, wild and dangerous. But on the right, that's the exact same system, but we've added D control. It's perfect. Just a smooth, clean motion that stops exactly where it's supposed to. And that is the magic of D control. It acts like a shock absorber for the system, taming those violent swings by looking at the speed of the change. It's the key to getting a really fast response without all that chaos. So by combining proportional and derivative, we now have what's called PD control. So we've solved the speed problem, we've solved the overshoot problem, we're done, right? Well, not quite. There is one last sneaky little problem that can pop up, even with a really well-tuned PD controller. What happens if there's some kind of constant force you're fighting? Like maybe a slight, continuous uphill grade or a steady headwind? The P control might not be quite strong enough to overcome it completely, and you're left with this tiny but permanent gap between where you are and where you want to be. It's called steady-state error. And this graph shows the problem crystal clear. See, we're trying to get the current in this circuit up to the target value. The PD controller gets it really close, but then it just flatlines, right below the goal. That little gap, that steady state error, it's going to stay there forever unless we do something new. And this brings us to the final piece of our puzzle, integral, or eye control. The best way to think about eye control is as the controller's memory. It sees that annoying little error has been hanging around for a while, and it starts adding it up second by second. It builds up this pressure, kind of like water behind a dam, until it has enough force to finally push the system that last little bit and wipe the error out completely. And would you look at the result? By adding that eye component, that persistent error is just gone. The system now climbs steadily and settles perfectly on the target. This is the secret to getting true pinpoint precision. So there we have it, proportional, derivative, and integral. 3 totally different strategies, and each one solves a very specific piece of the control puzzle. But when you put them all together, you get the absolute gold standard of the control systems world. This table really puts it all in a nutshell. You've got the P controller, which reacts to the present error to give you that fast response. You've got the I controller looking at the past, adding up all the old errors to get rid of that final offset. And you have the D controller predicting the future by looking at how fast things are changing to stop overshoot. Together, they are the PID controller. And here's how engineers actually decide which parts to use. It's a pretty logical process. You almost always start with P just to get a fast response. If that causes overshoot, you add D to dampen it out. If you have one of those nagging steady-state errors, you add I to fix it. And if you have both problems, well, then you use the full PID. So now that we've built this incredibly powerful tool, you're going to start to realize just how fundamental it is. I mean, this isn't just for cruise control or little electronic circuits. This is the invisible logic that is basically running the modern world. You see a massive industrial crane moving a multi-ton load with pinpoint accuracy? That's PID control. A drone hovering perfectly still in the wind, a 3D printer laying down a flawless layer of plastic, a robotic arm performing some delicate surgery. That is the power trio of P, I, and D making it all happen. So the next time you see a piece of technology operating just so smoothly and automatically, you'll know the secret. You'll see that constant battle against error, and you'll know all about the invisible intelligence, that proportional push, the integral memory, and the derivative foresight, all working together in perfect harmony to master our world.